So welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also see and appreciate the beauty in the simpler problems. So this problem comes from the MIT 2024 Integration Bee Quarterfinals number 3, and we tackle the first problem, which is the definite integral of the cardinality of a set consisting of the floor function of sine x, floor function of cosine x, floor function of tan x, floor function of cotangent x, beginning from x equals to 0 to x equals to 2 pi. Now, what this problem really entails is for us to find at every value of x, the cardinality of that set that consists of the floor function of x, sine x, cosine x, tangent x, and cotangent x. Now, before I go into solving this problem, I'd like to thank our subscribers. Thank you so much for your support. Your support really motivates us to keep going, and um, just coming back to you with the versions of solutions that we have for the problems that we present to you, Lord. And then also for our first-time visitors, what we do here at Everyday Mathematics is we go around and about and look for problems that may seem a little bit interesting, and then we share with you our version of the solutions. To those of us who are here for a second or third or fourth time but haven't subscribed, we do really encourage you to consider subscribing to our channel. Your support would really mean a lot because that will really give us the extra visibility that we need to keep going. So what is cardinality? Cardinality of a set is a measure of the number of elements of the set. For example, if we have a set consisting of elements x, y, and z, the cardinality of that set is 3 because we have 3 distinct elements there. If we have a set consisting of element x, 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 because we have the same element repeating 3 times, we would consider the cardinality of that set to be 1. And then if we had x, x, z, because we have 2 repeating elements, we would consider that 1, and then the extra one, which is the z element or the z element. And so the cardinality of this set would be 2. So that's what we're going to consider. Now, for our problem, we know what a floor function of a specific variable, for example, x, where it lies between 2 integers k and k plus 1, means that the floor function of that number or that variable would be k. That is the lower whole number integer. Yeah. So knowing that, and if we have the plots for sine x, cosine x, and tangent x and cotangent x, we see that there is variability. And we need to really split the 0 to the 2 pi. So 2 pi is here. And we have to split it into domains where we're able to distinguish the differences in terms of the number of elements, the specific elements within the set that we're given. For example, between 0 and pi over 4, which is here, we see that because sine x and cosine x are less than 1, they would all be 0, right? Because that's the lower integer. Right? And then tangent x, right? Tangent x would also be 0 because it's less than 1 at that point. And then beyond pi over 4, you see that it crosses, tangent x crosses, so it's about here, it crosses 1 and begins to be greater than 1. So we see that tangent x becomes 1 for a small duration until it becomes 2, and then it continues from here onwards until it crosses the 3, becomes 2, like that. So I would have to divide these domains into small subdomains. So would have to have, for example, this domain we would have to have from pi over 4 to pi over 2, and then from pi over 2 to 3 pi over 4, and so on. And then we begin to investigate these different functions independently. So let's say that we have 0 to pi over 4, pi over 4 to pi over 2, pi over 2 to 3 pi over 4, 3 to pi over 4 to pi, pi to 5 pi over 4, 5 pi over 4 to 6 pi over 4, 6 pi over 4 to 7 pi over 4, 7 pi over 4 to 2 pi. And for sine x, since sine x between 0 and pi over 4 is less than 1, that would be 0. Then from pi over 4 to pi over 2, again, is less than 1. We'd take that to be 0. The floor function of sine x would be 0. From pi over 2 to pi over 4, still under less than 1. And so the value of the floor function of that function is 0. From 3 pi over 4 to pi, since it's less than 1 at that point, it becomes 0. Now, from pi downwards, we see that the value of sine x is less than 0, so the integer lower than 0 is going to be -1, and -1, -1, -1. Cosine x in the first interval would be 0, and then from pi over 4 to pi over 2, it's still less than 1, so it's 0, and then it crosses into the negative domain, and so now it begins to be -1, -1, -1, -1, and then it begins now to cross into the positive domain from 6 pi over 4, and then we have 0 and 0. Tangent x, since it's less than 1 between 0 and pi over 4, we have 0, and then it crosses +1 at pi over 4, so it becomes greater than 1. And then at pi over 2, we have it coming from a negative infinity, so it's less than -1. And we know that at pi, that's when now at 3 pi over 4 is when it crosses -1. So in that domain up to pi, we have -1. And then it crosses 0 at pi. And so we have 0 greater than 1 at 5 pi over 4. And then from 6 pi over 4, we have it coming from negative infinity. And so it's less than -1. And then between 7 pi over 4 to 2 pi, it crosses -1 but 0. So in that entire regime, we have it to be -1. The same thing we do for cotangent x. And this is what we get. So what is the cardinality of this set at these different intervals? What does it tell us? It tells us that in this first interval, since all these are the same, the cardinality of the set there is 2. In the next domain, since again these and these are the same, so we have 2 distinct values, so that is 2. In the next one, since we have this and this being the same, so we have 1, 2, 3, so we have the cardinality of 3 in that regime. Here, since these are the same, we have 3 distinct. And here, since we have this being the same, we have 3 distinct elements. And here, since these are the same again, we have 3 distinct elements. And then here, since this and these are the same, we have 3 distinct elements. And here, since this and these are the same, we have 3 distinct elements. So essentially, our integral of the cardinality of floor function of sine x, floor function of sine x, floor function of tangent x, floor function of tangent x is the integral from 0 to pi over 4, where the cardinality here is 2. Here from pi over 4 to pi over 2 is 2. The rest of those regimes we have 3, 3, 3. And so we can now have add 2 times pi over 4, since these are constants. 2 times pi over 4 plus 3 times pi over 4, 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 3 times pi over 4. So we have 1, 2, 3, 4, 5, 6, 6 threes. 6 times 3 is 18 plus 220 plus 222. So we have 22 times pi over 4, and that means we have 11 pi over 2 as our answer. So this is the answer for this interesting problem. I hope you did enjoy following along. If you have any question, it's a little bit tricky, but if you have any question, please don't hesitate to leave a comment in the comment section. Thank you so much. Until next time, à tout à l'heure, la prochaine fois.